Welcome everyone to a brand new AI Research Bite, our very first of 2026. Thank you so much for joining us. My name is Marie-Lise and I will be your host for this session. For those of you who are new here, AI Research Bites is a series of short informative talks where we showcase cutting-edge research from ServiceNow's AI Research team. These sessions are open to everyone, especially those of you who want to stay connected with the fast-moving world of AI research. Today's session, we will have Rafael Pardinas presenting a 15-minute talk on PipelineRL, and we will follow that with a 10-minute Q&A where you can ask all your burning questions to Rafael. Before we dive in, let me share a few words about today's speaker. Rafael Pardinas is a researcher at ServiceNow AI Research, where he is part of the Frontier AI Research Program in the RL for Agentic Reasoning team. His research focuses on reinforcement learning methods for training LLMs with an emphasis on scalable and efficient training systems and on developing RL techniques to support reasoning and long-horizon agentic decision-making. With that, I'm thrilled to hand things over to Rafael. The floor is yours.
Hi, thank you, Marie, for the introduction. Let me share my screen. Hopefully, it's all clear. Thank you very much. All right. Hello, everybody. So today we're going to talk about PipelineRL, and which is a system and a paper that we released last year, a couple of months ago, that achieves twice the speed on policy RL training for language models. Now, perhaps let me go through the disclaimer, just to make sure that everybody knows that this is ongoing research, etc. And then let's jump into why should we look into using RL to train our language models. There's many reasons for that, but briefly, so the concept of the typical language model that we get in our hands is normally trained or pre-trained using imitation learning. So the model will try to generate responses that has seen already, or is going to try to imitate previous case scenarios. With reinforcement learning, on the other hand, we optimize for success. So the model will try to perform that task as best as possible. So it strives for that. We have seen this technique being used in most of the popular models or AI systems that we probably use daily. So, for example, the OpenAI reasoning models like 103 and so on uses that, and most of the really popular open source models as well, like DeepSeek, Kimi, Qwen, etc. And so the technique that he uses is reinforcement learning with verifiable rewards to achieve to unlock reasoning on these language models for tasks like math, coding, etc. So we optimizing for task success and not just imitation or pattern matching. But that creates a problem. So how do we scale this? That is a fairly complex problem. So let me give you an idea of how conventional RL works, so we can start understanding, how we try to solve it, or how we solved it. So conventional RL goes through all these steps. We have a data set that has problems or prompts. The problems we are looking at for our experiments, and in this particular case, are mathematical problems. So we send those prompts to the inference engine. That inference engine generates a completion, which is sometimes correct, sometimes not correct. Initially, it's going to have probably a high level of mistakes, so that we have to then verify those completions to generate a reward, which tells the model if it's doing good or not. Then with that reward, we put all those pieces together, and we have a rollout. Then we send that rollout over to the model, sorry, to the next phase of the system for training. So once we train, once we go through that training, we have a new set of weights, and we start the process all over again. And hopefully, after a few cycles of this repetition, the model will start generating the correct outputs. So that's the idea. Now, as you can imagine, all that is quite slow and costly. But there's also another reason for that inefficiency, and is how are we utilizing the compute we have in our hands? How effective are we using on using all those GPUs? So traditionally, when we train these systems, we create a batch of samples, which is a list of many samples grouped together, and we send it over to the GPUs. We might have a pool of them, many of them, say 8, for example, or 4. So those GPUs are gonna receive those samples and start producing completions. But some of those samples are way longer than others, right? So the GPUs are gonna take more time to generate those completions than with the shorter samples, meaning the GPUs that finish quicker are going to be idle, waiting for everything else to complete and then go to the next step. So there's a lot of idle compute potentially there, and in most of the cases is what happens. Now, the first question could be, why don't we batch more? Why don't we generate a lot more samples, and then we can take a lot of optimizer steps with all that data, right? We're used to doing that in other cases. And the problem with that approach is that it would be faster, but from the very first optimizer step, subsequent optimizer steps are going to start using stale data, because that data has been generated with all weights. So it's going to be stale already. So it's going to be faster, but that's not very effective. And let's not worry too much about the equation we see here, but the idea is, in order to generate data faster, we need to know how much we can learn from that data, meaning, how many rewards can we get from those samples, and how fast we can generate that data. So here, the trade-off is we have to choose between going fast or being effective. So generating a lot of samples or generating fewer samples, but very good quality. But then for PipelineRL, we thought, why can we not do both, right? There's no reason why we couldn't do both, or at least that was our premise. And the first thing we used to solve this problem was with in-flight weight updates. And that essentially means that we have the training and the inference GPU pools working simultaneously, working at the same time, generating data and consuming that data. So when the trainer completes one of the an optimizer step, we send those weights immediately to the inference servers, so they generate more data. And so those weights are swapped straight away on the inference side, and data generation never stops. We keep generating data and training with that data continuously. So that fixes the first problem. So we don't have these synchronization issues that we were talking about. Everything happens at the same time. We don't have to go in that costly loop. And we have maximum GPU utilization, because we fill those GPUs with as much data as we can have, because we don't have any problem generating data constantly. It's going to be fresh, as we can see here, because that is the next step. We can achieve fully asynchronous on-policy training, because we don't have any batch barriers anymore. We can fill those GPUs with data. We can generate and optimize the weights at the same time. So we have those two steps overlapping. And what that means is that we are constantly generating fresh data, or near on policy data, because we have new set of weights always available to generate more. So that essentially gives us learning at scale. So we can continuously improve the model and scale, potentially, well, as much as compute that we have. So I showed you earlier what a conventional RL training step looks like. This is what the pipeline RL one looks like. So what we have on the left of this image is the actors, which is the inference servers. They are constantly generating data. Those actors are going to be creating pools of data. We send that over to the next step, which is, we'll call it here the preprocessor. What it does is we do the verification that we did previously. So we compute rewards for that data and log probabilities as well, depending on what algorithm we want to use for our loss computation, for the policy loss computation. And then once we have all that data, as we saw at the beginning, we have the same type of rollouts. We packet all those rollouts and send them over to the trainers. So the trainers can continuously pull from that source of rollout data and update the weights. Once we have a new set of weights, as we see here on the right-hand side, we send immediately, we broadcast those weights over to the inference servers. And the cycle continues, non-stop, as we said earlier. So after all those things being put together, we can see our results show that we achieved twice the speed that we have in conventional RL, even though we were using the technically more effective ways of training, or faster ways of training, not effective. So we went to optimize the steps all the way to up to 32, and we see that not only we are faster, but also as we increase the number of optimizer steps, the training becomes unstable, as we see in this curve and we see in this depot over here. Let me show you a quick demo that shows this. So we see here the batch size is constant with PipelineRL, always. With conventional RL is not. We see the samples steadily increasing on both, but on PipelineRL is a smooth curve of samples being produced. The throughput is really good. And then we see the rewards going up as we expect on a healthy training cycle. Right. So then what do we have with all this? The end goal then is that we have the same sample efficiency as we do with conventional RL, but we are not just faster and being more effective. We also have more efficiency per sample. We match the on-policy baselines, as we saw initially, with one optimizer step per RL step. So we are matching on rewards versus samples, but also matching on time. We being also way faster, and all that without any degradation on the training evolution. So even though we are slightly off policy at times, and that is with twice the speed in the worst case scenario. Since the release of PipelineRL, we have seen massive adoption in the community, to the point that is becoming the standard on RL training at scale. As we can see in some of these images, one of them is from the LLM, which is one of the most popular inference engines. And we see that they already implemented the PipelineRL premise into their engine. And we see a lot of the big names in the community, the RL community, LLM community, talking about PipelineRL and how revolutionary in many ways as seen on to speed up training. So the takeaways to finish with are that we have a new algorithm that using the same resources, we can achieve results in half the time, twice the speed up. We have no waste of GPU. GPUs are never idle, they are always working. We have weight updates, so in-flight weight updates, so the data is always generated with fresh set of weights, and we are matching the state of the art on the most popular benchmarks. So we can see here where our code is, and here the paper review wanted. Thank you very much.
Thank you, Rafael. Thank you for this great presentation.